Okay, afternoon, everybody. Today I'm going to speak about a new project, a new fellowship that's I've started, which is going to be a 5-year project, and it's in collaboration with Leonardo UK. The subject of the fellowship is in the area of intelligent multifunction radio frequency systems. So today I will talk about the research vision of that work and what I propose and what I'm hoping to achieve within that. Mention the industrial partnership that we've established for this project. And then address the first question you might have, which is what is an intelligent multifunction RF sensor? Mention the research that myself and the team that I work with have been able to complete to date, of which most of the group here will be aware of, but kind of reviewing where we're at. And then talk about some of the plans for the 5-year period overall, and then provide some general conclusions of what I've presented today. Okay, so what's the concepts here? Well, the research vision I have is to try and use some experience I have in both industry, government, and academia to position yourself as a leading expert in the field of RF sensing. These statements are all strong, bold kind of claims, because this is what you need to do, I think, when you're pushing to achieve such funding. So apologies for being so bold in a way. So I would like to use my cross-disciplinary knowledge with the aim of solving real-world applied problems. So it is very applied, it's experimental by nature, and it's looking to address end-user needs and both industry and government challenges. Currently, the siloed section shown in the bottom left diagram there shows that radar, electronic surveillance, communications, and other forms of maybe electronic warfare are all very separate activities completed by separate hardware, separate software, and reduced or very little interchange between them in the current status. So what I'd like to do with this research fellowship is to try and break the boundaries between these RF sensing disciplines by the development of multifunction solutions. So this means that the same piece of hardware or an algorithm is able to intertwine these modalities such that you can now intelligently or in a clever manner get the most out of a potentially smaller size, weight, and power solution. As you know, kind of constraint, particularly on, I guess, airborne platforms or man-portable platforms, is often going to be that size, weight, and power. So if you have to have a separate antenna, a separate ADC, a separate DAC, a separate RF chain for each of these example set of devices that all harness radio frequency signals, then you're going to increase that requirement of size, weight, and power. So this multidisciplinary device that can perform multiple functions is attractive in that manner. In order to achieve that, I'd like to push and try and establish the UK's first, in an open academic environment, radar, electronic warfare, and communications testbed based around a systems on a chip architecture. This is an experimentally focused vision and project, and we'd like to demonstrate how multifunction adaptive RF concepts, such as cognitive radar, can be proven for the first time. Now, cognitive radar, of course, is a topic of much debate within that community about first defining it and then secondarily showing it in action. Many have worked in this area. We're not claiming the definition necessarily, but we certainly would like to start increasing the technology readiness level and experimentally demonstrating algorithms and concepts that are in the domain of either adaptive, intelligent, or cognitive, depending on your definition. The industry sponsor that I'll be working with in the fellowship is Leonardo UK, and they are a key partner in this project, and all of the work is tightly entwined with that partnership. Leonardo Electronics produces integrated solutions for sensing and protection, representing, I guess, that radar and then that electronic warfare side of the coins. So that includes radar and defensive aid systems. They have a strong interest in multifunction RF systems and software-defined functionality, because I think Leonardo, as well as many other technology companies in this space, believe that that is going to be the future for the hardware and software. The convergence of today's discrete radar, electronic warfare, and communication hardware platforms is something that of great interest, and the sponsorship and collaboration represents how significant that interest is. And the research itself bridges between the Luton-based teams within Leonardo and the Edinburgh-based teams that represent the two sides of the sensing problem, I would say. And that kind of shows how the boundaries between the different modalities can be potentially broken down and allow for the development of multifunction concepts. From the get-go of this project, a new PhD was established in partnership with Leonardo, and Jacob Fromage, who will be presenting here at the UCL Radar Group and working between UCL and Leonardo, represents that new link. And as part of this work, we aim to complete future joint trials together, which is a real enabler for us here at UCL, that we can access these large-scale trials that an aerospace prime is able to put on, which is an excellent opportunity. The multifunction sensors, everyone in my direct team is very much aware of what I'm going to say here, but just for the benefits of those who haven't seen this, UCL has developed a system called Arresto, which is based around the Xilinx RF system on a chip architecture. It was initially funded by the Ministry of Defense via Defense and Security Accelerators, a couple of different phases, as well as other spin-out funding opportunities. Fundamentally, the system shown in the middle there is based on a Xilinx system on a chip architecture. What we've created in the first instance is able to operate as either an active radar, a passive radar, a joint radar communications system, or electronic surveillance sensor. That's not an exhaustive list, but some key examples of what we can achieve with the device. It's able to also operate in a multi-static manner, represented by the bottom left geometry, which allows you to transmit and receive from different locations using our prior experience and current hardware on how to trigger and synchronize RF sensors. Many open questions still exist in terms of how to use all of these modalities and equipment, in terms of when to use each of the modes. So you now have a device that can be a multifunction device. So when should it be active? When should it be passive? When should it prioritize this range of modalities? And how do you fuse sensors, data from these different modes? And can cognitive radar concepts be implemented in real time on such hardware? And where does the decision making happen in a processing pipeline, I guess, that ranges from FPGA to ARM core to maybe slower time offline processing attributes? Why the system on a chip? Well, I kind of believe that this is step change in hardware is capable of enabling the development of a diverse array of research, including communications and radar or electronic warfare concepts. The focus is on the development of a single platform that can address research in multiple areas. So because of the good work that both Dr. Colin Horn and Dr. Niall Peters has completed with me, we're able to operate this as a multi-static coherent sensor. We're looking at creating adaptive and cognitive modalities, looking at how we can have a multi-role device that is intelligently switching between modes, either proving the concept via offline processing or moving towards real-time multi-role switching. We've completed passive radar experiments with this, using both Wi-Fi or DVB-T illuminators, and proven detection of a variety of targets. We have some novel waveform design work that we've been implementing recently that may allow, for example, a reduced probability of detection of your waveforms or enhanced operation in congested environments. And then shown in the figure there, an antenna array that was initiated through a collaboration through Dr. Amin Amiri has allowed us to perform beamforming on receive with our configuration. So yeah, a couple of those capabilities were then output via a set of papers here through a variety of team members' collaborations and the hard work everyone's been put in. Dylan processed a multi-band Doppler classification result, looking at how different frequency bands can allow for detection and classification of drones. Working with Murat Tamiz and Professor Christos Mazouras, Niall and Colin achieved some experimental work on radar-centric joint radar communications, and that work is now a growing piece of this puzzle. We've shown real-time detection and classification of LoRa, which is an Internet of Things protocol, using an implementation that works on the FPGA itself, and that was shown in that IEEE Access publication. And there was an active and passive result shown that came from a simultaneous measurement, and that was at the International Radar Symposium in 2022, showing how both modalities can operate in unison, and you're able to either detect a target in active or passive mode. And we'd like to grow that more analysis in that space as well. And multi-static experiments showed how, through collaboration with Murat Tamiz, what the benefits are of hybrid multi-static radar network deployments. And then the phased array, which I showed in the previous slide. So one of the modalities is electronic surveillance, but the purpose is to receive signals and make sense of them. Here I'm just showing a wideband capture, which is an interleaved measurement of 3 channels, 2 gigahertz instantaneous, but 6 gigahertz when interleaved, and in total, with some loopback signals of a variety of shapings, either tones or chirps or intermittent signals overall. And this represents how we could generate data sets that are representative of what that challenge is, which is detecting and classifying many signals instantaneously. In reality, you would expect actually many signals overlapping on top of each other here, and really congested bands with a mixture of communication signals and radar. So this is quite a benign environment. We would like to start capturing either in environments in the real world, in situations where there's many illuminators, maybe on a coastal littoral environment, but we would need to have our X-band front end in order to capture, say, maritime radar setups there, or generate synthetic environments via creating many signals overlapping with a secondary RFSoC or a signal generator to make a representative as much as possible situation where we have to then detect and classify the signals. Ryan White, the DSTL PhD, will be working on the area of electronic surveillance, and will harness this hardware to achieve exactly that, and have a blend of modeled, experimental work, and then classification processing methods being leveraged. The multi-static work at UCL has been going on for some time, and from our experience of using systems like NetRad and NextRad, we're aware of what's needed to create a synchronized, clocked and triggered solution as a multi-static radar. Here, through the hard work of Piers Beasley, we were able to create GPS dissonant oscillators that can synchronize and trigger, or subsystems that are based on them, our RFSoC solutions. Niall and Colin did some excellent work then as well on making sure we can use those subsystems with the system on a chip architecture, such that we can now deploy in a multi-static manner. This means we can detect and classify targets in different varying geometries, at varying angles and varying deployments, and use our N nodes deployed in a certain configuration. These clocking and triggering solutions were recently deployed at the University of Birmingham with their 2 radars that are established on the roofs of University of Birmingham, which shows how it really is a useful subsystem that Piers has created there that can be other teams can leverage and use, and is agnostic to the sensor that it works with to a degree, which is a great achievement. And we hope to use these further in future experiments. some results here showing monostatic and bistatic measurements of a person walking away and coming back, just proving the concept that we can deploy in such a way. So this is the tip of the iceberg of then all the degrees of freedom that you have once you then have active modes, passive modes, monostatic, bistatic, multistatic opportunities. Briefly on the subject of radar communications, well, through some collaborations with Professor Christos Moussouras, we've been looking at this area more recently and looked to develop some LPI waveforms that allow you to both sense and communicate. An example of this, is index modulation. This means you change a value, a parameter, on a pulse-to-pulse basis, and those indexes are the communication signals fundamentally. The parameters we've selected are the central frequency of your chirp and the bandwidth of your chirp, as well as sending this simultaneously on two different polarizations. And some of the examples being shown here. You then can have achieve both sensing and communications. Other parameters could include also chirp direction. And in some cases, you create a trade-off between your priority of communication and your priority of sensing. And future research will look to evaluate how that trade-off can be tuned in real time in experimental scenarios. So yeah, long-term kind of big ambition is technology demonstrators are vital in de-risking novel concepts and providing real experimental validation of ideas is what we want to push forward in the field of multifunction RF sensors as well as intelligent RF sensing. I think that captures cognitive as well. Use the developed RF testbed to establish new collaborations with industry and academia, host scientists, and deploy joint experiments and use the equipment as much as possible for what it's able to achieve now, and create new channels of research and development in this domain that will lead to high impact, etc. These are all great aspirational pieces. So fundamentally, what do I want to do in this fellowship though? Well, it's broken down into 4 work packages. I'd like to work on the adaptive RF sensor mode selection initially, so how we can toggle between modes or run these modes in parallel, and then make some decision making between them. The second work package looking at multistatics. The third, array-based processing. And then the fourth looks at the first 3, but starts bringing in a challenging, congested, contested environment, and that would be completed in conjunction with the NRO. So we hope that this will represent the first UK's cognitive intelligent RF testbed based on system on a chip. And we have currently 4 8x8 RFSoCs and 1 16-channel RFSoC, which has just recently arrived at UCL. That's a newer variant, that's a generation 3 board that has higher ADC and DAC rates. But as you can see from the picture here, we have a custom daughter board and then granddaughter board design that works with the generation 1 8x8 RFSoC, which is the ZCU111. For this 16-channel version, this would need to be redesigned or a different solution would need to be created, which is a significant proportion of work. So you need to create a roadmap of when and how we can achieve that. We have an antenna array, which has been shown in previous pictures, and one of those is operational, and the second one is kind of mid-development, mid-deployment, as we're assembling and creating the required power and other solutions needed to have that operate. These are receive-only arrays currently. Just on this work package, very briefly, work package 1 is this changing modality. So when to be active, when to be passive, or when to prioritize comms, when to prioritize sensing, and trying to put that choice closer to the front end of the sensor as possible. And look at intelligent mode selection in challenging scenarios. Dr. Colin Horn is involved in the NATO SET panel on cognitive radar, and our hardware represents a potential example demonstration case for some of the experimental concepts that are being developed. Work package 2 is to enhance or follow the thread of how multistatic radar can enable another degree of freedom in multifunction RF solutions. As you can imagine, distributed RF sensing swarms are conceptually things that are being thought of right now and are not too far away in the near future. So how would you then use at scale many multifunction sensors, and how do you maximize what you want to achieve through your multi-static deployments overall? Leveraging some of the timing and triggering solutions we have and our prior experience of multi-static radar processing. Third work package is array-based processing. So fundamentally, we're interested in if you have a large singular array and scale that and drive a single array solution with many digital systems behind it, you have a higher singular capability. Or you could go with a distributed solution that has a lower spec array or a lower spec beamforming capability, but provides multi-static sensing concepts. And there's a trade-off space there. And understanding how that trade-off space can be quantified is something of interest. And then, as I said, the fourth work package looking at all three, but then in congested scenarios, and with the objective of generating kind of resilient sensing modes that can maintain operation despite adversarial system actions or benign, nevertheless annoying interference from, say, communication bands that are adjacent to your sensing bands. Some of the themes here might be adaptive beamforming or novel waveform design or fusion of sensors. And that will leverage kind of the aerospace prime's unique knowledge on this area. So I had a quick run through the plans of the research, and I hope to develop new modes and enhance current modes to deliver research outputs on each of these. We have many new team members joining, 4 since September 2023, all which will leverage the testbed and lead on unique aspects, be that electronic surveillance, multifunction, joint radar communications, or adaptivity. And I'm keen for collaborations and open to discussing how we work best together. And I certainly need to acknowledge Dr. Niall Peters and Dr. Colin Horn's excellent hard work getting us to this point. It's been amazing hard graft from them to achieve everything I've talked about in this presentation. There's a slide that you're asked to throw up at the end of some talks and explains the scheme itself, and you can follow and see links to understand further about these opportunities. Yeah, thank you for your time, and I'm happy to take any questions.